Welcome to this video lecture on pump specific speed. In this lecture we'll talk about what specific speed is, how we use it, and how we calculate it. So go ahead and take a look at your screen. The picture here has actually nothing to do with pump specific speed, but I thought I'd show it because it shows an iconic type of pump, just a hand pump that you'd get, that you would use to get water from a well, like out on a farm or something like that back in the day. I thought I'd show it just because it's such an iconic pump. People have seen it. It might be interesting to take a look at how it works. So the idea is this. You have this kind of hand pump here that moves this piston rod up and down. So it's a little lever here that moves that up and down. And key to the operation of this pump are these two check valves. One here in the piston and one down here that leads into the pipe that goes into the well. These kinds of pumps only really work for near surface water, so wells that aren't deeper than, let's say, 30 feet deep, because they rely on atmospheric pressure to push the water up into the pump. So the idea is this. Let's imagine that the piston here is all the way at the bottom, so it's all the way down. And then what we're going to do is we're going to start to lift up that piston rod. In that case, this check valve would be closed, heading upward, and this check valve would open, and it would create a low pressure region in this cylinder region here. So it'd be low pressure, and what would happen is the atmospheric pressure would push the water down through the pipe and up into this chamber. And so the water would then be in this chamber, and then as the piston rod comes back down, this check valve will close, this one will open, and so then the water can come up into this region, just the location above that check valve. So it would be in this region. And then, so you'd get water coming in here, and as that piston rod goes up further, that water will be lifted and then moved to the water outlet. So that's the idea behind here, is it's just a positive displacement pump. We're changing the volume of this cylindrical region here, and as well as up in here, by moving that piston up and down. And the operation of it relies on these check valves. These check valves have to work in order to move the water from one chamber to another. So anyway, nothing to do with pump specific speed, but I just wanted to show you an example of a very iconic kind of positive displacement pump. All right, so let's get into the material for today. We're going to talk about pump specific speed. And let me just say, starting off, the reason, so what pump specific speed is used for is to determine what kind of pump design would be most efficient for a given operation. So what I mean by pump design is whether a radial flow pump or an axial flow pump would be most effective, or maybe something in between, given your requirements for the head rise and rotational speed and flow rate, that kind of thing. So it just gives you an idea of what class of pump would be most effective. It won't tell you exactly what individual make and model number is the right thing, but just what general class of pumps is most efficient for your given conditions. And so the key parameter for calculating specific speed is right here. In fact, N is our specific speed, and it's defined as the rotational speed of the pump, omega, times the square root of the flow rate through the pump, Q, divided by G, which is the acceleration due to gravity, and H, which is the head rise across the pump, all raised to the 3/4 power. So again, in your particular application, presumably you would know what your requirements are for flow rate, head rise. The rotational speed is often dictated just by the motor that drives the pump. A lot of motors have predefined speeds, like AC motors might operate at close to 1800 RPM or maybe 3600 RPM. That's just the way that many motors are designed. And so omega would also be something that you presumably would know. This kind of weird combination of parameters comes about from actually combining together two dimensionless pump quantities, the dimensionless flow rate and the dimensionless head rise. So it actually comes from the following. So here's the dimensionless flow coefficient raised to the 1/2 power divided by the dimensionless head coefficient raised to the 3/4 power. These dimensionless quantities are covered in a different lecture. But basically this is a dimensionless flow rate and this is a dimensionless head rise. And when you combine them in this manner, what happens is the pump diameter disappears. It divides out. It doesn't show up in the any longer because it just divides out, and that gives you the specific speed. And so if I just substitute in for those parameters for the dimensionless flow rate and dimensionless head rise in terms of its dimensional parameters, you get this expression. Okay, so this capital Phi and psi quantities are given in a different lecture. And so what's done then is different classes of motors, of course they all have their own individual head curves, right? So just a refresher on that. So the head curve would look something like this for a particular pump, and then the efficiency curve that corresponds to it would look something like that. So that would be the efficiency. And then we had talked in a previous lecture that that's the best efficiency point right there, right where the efficiency is the highest. And so what happens is these different kinds of pump types, the head rise and flow rate at that best efficiency point is calculated for a particular rotational speed, and then the specific speed is calculated for that. So that's accumulated for many different kinds of pumps, and from those calculations, what you find is you start to see patterns, right? So you'll find that when you're dealing with high flow rates and low head rises, those tend to be axial types of pumps tend to be most efficient under those applications. When you want a lower flow rate and a higher head rise, then the radial style pumps tend to be most efficient for those applications. So you'll find that the best efficiency point changes from high flow rates for axial style pumps to lower flow rates for radial style pumps. And so you start to see this kind of pattern, and when you look at this for lots of different pumps and kind of categorize based on that, you'll get a plot that looks something like this. So this is a plot showing the specific speeds. So a specific speed down here. The one on the bottom here is using that formula. And then you'll see the different pump types or impeller types up here on the top. So over on the high specific speed side, you have axial flow kinds of pumps or impellers. And then at lower specific speeds, you have radial flow, more like the centrifugal style pumps here. And then in between, you have mixed flow. Here you can see, for example, there's a kind of a combination of axial and radial components to that kind of mixed flow pump. So again, the idea here is that if you calculate the specific speed, and let's say you get a large value and you're out in here, let's say it's a value of 4, then an axial flow style pump would be most efficient for your operation. Doesn't mean you couldn't use necessarily a radial flow pump. It's just not going to be as efficient. This just helps you kind of narrow down what pump class would be most effective for what you're trying to do. Okay, and you can see that this sort of makes sense because you'll get a large specific speed if you're dealing with high flow rates and low head rises, which corresponds to axial kind of flow behavior, right? These kind of axial flow pumps we've talked in a different video, they tend to be most well suited for high flow rates and low head rises, whereas radial flow style impeller or pump here, they tend to have higher head rises and lower flow rates, so they'll be at a smaller specific speed. Okay, so that's the idea. Now you'll notice that there's another formula here, this NSD here. This is still specific speed, but it's given in a dimensional form. Up here, if you are careful with your units, it's dimensionless. But down here, it's actually dimensional with these specific kinds of units for those quantities. So omega here should be in RPM. The Q here should be in gallons per minute. H should be in feet. And this will give the dimensional form, and that's what this axis is up here. So it has a weird combination of units. But if you calculate it in this way, then you would use this axis up on the top. And the reason that's done is because in practice here in the United States, these are a common set of units that people use for quantifying parameters related to pumps: gallons per minute, feet, RPM. So rather than force people to convert to radians per second and do the unit conversions, they just define specific speed in this weird combination of units. So this formula corresponds to this one, and this one, where it's actually dimensionless, goes all the way down here. So I'll make a note here, this is dimensionless, because it's formed from these dimensionless quantities up here. So specific speed, again, just allows you to figure out what class of pump type is going to be most efficient for your given operation. All right, so let's see if there's any additional things I wanted to say. If you wanted to convert between the dimensionless and the dimensional specific speeds, the conversion is the following. So let's see here, the dimensional one is 2,733 RPM, gallons per minute, square root, all over feet to the 3/4 power, times the dimensionless specific speed. So if you wanted to do that conversion, there it is. All right, let's see here. So some rules of thumb I guess I have here. Just relating to pump types. Rules of thumb. Positive displacement pumps are generally used for small flow rates and high head rises. So positive displacement pumps, Q small, H large. So large head rise, small flow rates. Centrifugal pumps, these are a type of dynamic pumps. So centrifugal pumps are for moderate Q and moderate head rises and large flow rates. Okay. For very large head rises, sometimes you'll actually put multiple pumps in series, and so that's like a multi-staged kind of pump. So we'll just make a note of that. So it's not uncommon to see pumps put into series, so you can get very large head rises. So each pump adds its own head rise, and so by the end of a bunch of different pumps, you'd have a very large head rise that would occur. And then the last rule of thumb is axial flow pumps. Those are for high flow rate and low head rises. And again, you can sort of figure those things out just from the specific speed, since the specific speed, again, has the flow rate in the numerator and the head rise in the denominator. So large specific speeds means large flow rates, smaller head rises. Lower specific speeds correspond to lower flow rates, higher head rises. That's really all there is to say about specific speed. Again, it's just a way to determine what class of pump type will be most efficient for your given application. Okay, so we'll end it there.